Good morning, one and all. As promised, I have the problem that Archimedes encountered. Once he got over his excitement, he set out to solve the issue. Spoiler alert, we do not know whatever the crown was made of. It seems to be lost to history. The story could be true or could not be true, but in the end, we know that Archimedes came up with his law of buoyancy and that we are able to determine the densities of objects from that. So let's take a stab at it. When in fluids, particularly with buoyancy, they'll talk about weighing objects in air and then weighing objects in a fluid. In physics, we have a particular kind of idea in mind for that. And it involves something called a hanging scale. If you've been to the supermarket and they have those scales with the basket underneath, right? And you put the thing in and the little thing. So that's what's going on, right? There's this scale that's reading something, right? And the thing that it's reading is hanging down, right, from a string. That's pretty much what we're talking about when we weigh something in air, okay? The scale, right, there's like this tension that's acting upwards, right, pulling up on this object. Gravity's pulling down. Those two forces are canceling each other out, but the scale is going to read the tension in the string. So when we weigh something in air, right, we just get its weight, right, as its mass times g. But if we weigh something in a fluid, okay, there's going to be that tension acting upwards. There's going to be that gravity acting down. But now that it's surrounded by the fluid, the water, we're going to have this extra buoyant force that's acting up on it. So notice here that when we're weighing something in air, we don't acknowledge the buoyant force acting on it. The density of this fluid, this water, this fluid with specific gravity is so much more than water, okay? Or in this case, less than air, that we don't have to worry about the buoyant force in air. Something we do in physics quite often. Unless we're talking about like helium balloons or hot air balloons, right, where the density of the material inside the balloon is less than that of air, we're not going to worry about the buoyant force of air acting on it. What the heck is specific gravity? That's a fancy term for the ratio of something with respect to water. So remember, the density of water is 1,000 kilograms per cubic meter. And so if this thing has a specific gravity of 0.7, that means that the density of this fluid is 700 kilograms per cubic meter, right? 0.7 times 1,000 is going to be 700. So anytime you see specific gravity, just multiply it by 1,000 and you've got the density of the object. All right, so what do we know? We know that this object weighs 300 newtons when it's weighed in air, and we know that it weighs 200 newtons when it was weighed in this fluid. Where did the 100 newtons go? Why does it weigh less in the fluid? What's holding it up? Gravity acts down, tension acts up, but what's the additional force we have there when it's submerged? It's that buoyant force, isn't it? Okay. So if the difference, right, if it's 300 in air and 200 in the fluid, that must mean that my buoyant force is 100 newtons, right? It's a 300 minus 200 newtons, that difference that arises. So there was an extra amount of force that was applied. We know it's 100 newtons, but we also know that that buoyant force has to be equal to the following. It's got to be equal to the density of the fluid that got pushed out of the way, G, and then the volume, again, of the fluid that has been displaced. This is where things in these problems get a little bit tricky. We know, okay, the term is immersed here, okay? Immersion, or that term immersed, means that the object has been put completely inside the fluid. If you have something that says floating on the surface of the ocean, right, and it says that it's only 1/4 of its volume is submerged, right, then you would take 1/4 the total volume of the boat, and that would be the amount of fluid that gets pushed out of the way. Here, when it either says completely submerged, or immersed, or completely under the surface, or something like that, then we know something about the volume of the fluid that got displaced and the volume of the object that went in. What has to be true? Those have to be the same. Good job. Right? Because it's completely surrounded. So for this particular problem, we know that the volume of the fluid and the volume of the object have to be identical. Okay, well that's going to help us. Okay. Find out what's going on here. What do we know? We know the buoyant force. We know the density of the fluid. We know what planet we're on, and we can solve for the volume of the object. That's going to help us to determine the density of the object, which is going to help us to determine what the object is made out of. So we know this is 100 newtons. We know that this is 700. We know this is 9.8. Again, if I put everything in standard units, I'll get standard units out. And so what would the standard units of volume be? Yeah, meters cubed. Good job. I have 1.46 times 10 to the minus 2 cubic meters. All right, we know the volume. We're going to find the density. So there's my volume. They asked me to volume, so I better box it. Density is mass divided by volume. So I've got the volume. How am I going to find the mass? Ooh, divide what by gravity? The weight in the fluid or the weight in air? Air. Yeah, it's air, right? So this is back from, I don't know, chapter 4, right? If we know the weight in air of an object, its normal weight, okay, then all we've got to do is divide by little g to get that mass. So if we divide this by little g, we'll have the mass. Don't know why I wrote it again, I did anyway. 30.6 kilograms, that's a 6. And then I can go ahead and do 30.6 over 1.46 times 10 to the minus 2. And I will get standard density units, 2.1 times 10 to the 3 kilograms per cubic meters, which is pretty darn close to gold. So in the sake of this example, the crown was made very nearly of gold. The key thing to remember about Archimedes' principle, buoyancy, is it's the density of the fluid that is being displaced that matters. And then the volume of fluid will depend on the situation in your problem. After that, it's an equilibrium problem. Straight out of chapter, what was that? 9, 10, something like that. All right, let's play with some balloons. Because we can't do buoyancy without talking about balloons. Because balloons are some of the best objects in the world.
If we place this helium balloon inside a glass jar filled with air, it floats to the top.
Yeah.
If we replace the air in the jar with helium, what will happen to the balloon?
Okay, so why does the balloon float? Okay, so it's surrounded by air. So what? Okay, so the helium inside the balloon is less dense. It's lighter than air, isn't it? So this means that the balloon, right? What is the balloon doing when it's filled with helium? It's pushing air out of the way. And the buoyant force does not depend on the helium. It depends on the fluid that got displaced, in this case, air. And since the weight of that air that was pushed out of the way is more than the weight of the helium in the balloon, the buoyant force is going to be winning. So now they're going to replace all the air that's around the balloon with helium. What's going to happen? Going to go down? Why would it go down if it's filled with helium?
Because water has a lot of hydrogen in it.
No, there's no water here.
The buoyant force will be equal or?
Okay, so the buoyant force is going to be kind of canceling out. So what's going to pull it down? What's the balloon made of besides helium? Latex, right? The balloon itself, right? So that material, right, inside and out, buoyant force is basically going to cancel itself out. Weight of helium inside, weight of helium outside is going to be the same. And it's going to be the latex of the balloon that pulls it down. Gravity will win, pulling it to the bottom. Okay.
The balloon sinks to the bottom. If the jar is now lifted off the table, what will the balloon do?
Okay, they did not explain this very well. The first picture I got in my mind is, whoa, right? And then free balloon. No, he's gonna lift that jar up like very slowly. Just vertically straight upwards, okay? So if he moves that up very slowly, where is the balloon gonna end up?
Going up slowly?
Kind of going up slowly, but like where? Like halfway up the jar, top of the jar, bottom of the jar? Where do you think?
Probably the bottom.
Probably the bottom?
Because the air is still at the top.
Okay, so there's helium in the jar, right? But then there's air directly below the jar. So as this thing comes up, the balloon should stay right at that interface. Floating like a ship on the ocean.
It floats at the bottom of the jar.
Just enough.
Tip the jar to let the
To
helium
keep it
escape.
floating.
The balloon floats back to the top.
And now they'll replace the helium with air, letting the helium out, replacing with air. So with that balloon floating down there at the bottom, it was like a boat on the ocean. A boat only has to displace enough water to equal the boat's own weight. And then it'll float. Because the forces are all balanced right there. All right. So let's do another example of this time with balloons. Let's say that you want to induce competition here in Fresno by providing cheap, reliable internet access to the masses that Comcast and Xfinity can't, right? And so your grand plan is to take a broadband internet tower, kind of like a 5G network tower, but instead of having like a bunch of towers all over the place because of line of sight issues in buildings, you decide that you want to float your antenna above Fresno on a big balloon. Let's calculate how much helium we would need in order to lift a broadband antenna up above Fresno. So we're going to make some assumptions here. First of all, I went out and found out the mass of one of these antennae. Okay, they are approximately 4,000 kilograms or 4 metric tons. Okay, so this is big, right? It's a big antenna, big load. I then started doing some research into like how big of a balloon, like what kind of material, how big of a balloon is necessary for a payload like this. And believe it or not, there are companies that make balloons for this, okay? Not specifically for internet access, but for like scientific research, floating things way up high in the stratosphere. And I found from the website that in order to hold up 4,000 kilograms of payload, the balloon itself, not filled with helium, just the material of the balloon is 600 kilograms. or approximately 1,200 pounds. Like so these balloons are made out of basically this garbage can material, this plastic right here. I think it's like a polypropylene film, okay? This stuff is like really puncture resistant, right? It takes a lot of effort to really kind of get through it unless it's a really sharp object. But it's really, really thin. And the balloon is actually made out of something that's a little bit thinner than this. It's pretty tough, but it's really thin and light. So imagine 600 kilograms of garbage bags, right? This is gonna be a big balloon, right? So we want to calculate how many sad clowns are going to be in Fresno. How many birthday parties are going to go uncelebrated because we're going to empty out every dollar store of all of its helium, right? How much helium are we going to need, right, in order to get this thing to float? And we're just going to float it right at Fresno's sea level, okay? We're not even going to talk about trying to get it up further, which would require even more helium. So this is like the minimum amount, right? Okay, so let's see here. We are going to be floating something. Floating means equilibrium, and so let's see. I'm gonna draw a free body diagram of the balloon. Like it's kind of the central actor. It's the thing that all the forces are acting on, right? And so what are the objects that are pushing or pulling on this balloon? Name one.
Gravity.
Okay, so gravity we know is pulling on the balloon. But we got to be really careful about what we mean by that, right? Because there is the mass of the balloon material itself, right? The 600 kilograms of plastic sheeting, okay? And its weight, so it's being pulled on by gravity. And then there's the antenna, right? The payload that's pulling down on that balloon also, dangling below it, okay? Do we have any forces that are acting up? Yeah, buoyancy, right? That's what makes balloons be happy and float and go up and escape and do all that kind of stuff, right? There's actually one more force of gravity that's acting downwards. It's one that everybody always forgets to take into account. What's inside the balloon? Helium. Does helium have a mass? Yeah, we usually don't think about it because it's lighter than air. But there's going to be a lot of helium here, right? So we've got to make sure that we take into account the mass of the helium that is inside the balloon and the fact that gravity is going to be pulling down on that as well. So we've got the shell of the balloon, we've got the gas inside the balloon, and we've got the payload all pulling down. And then we have buoyant force acting upwards. So if we do the equilibrium statement here, where we add everything up to zero, we just want to float it, then I'm going to have buoyancy acting upwards, and then all of these gravities acting downwards. So helium time. Okay, so there we go. Let's see. Do we know the mass of the balloon? Yes. We also know what planet we're on. Do we know the mass of the antenna? Yes. Do we know the mass of the helium? Well, okay, yeah, we can like look at periodic table and find atomic masses, but like, isn't the mass of helium going to depend on how much helium we put in there, right? So, okay, well, we'll get to that in a second. Buoyant force. Well, we know the buoyant force is going to be the density of the fluid displaced. And what's the density of the fluid being pushed out of the way by our balloon? What fluid is being pushed out of the way? It's air. Times G times volume. Okay, so this is volume and air pushed out of the way. We'll just leave it as that for right now. Okay, minus the mass of the balloon, which we know. Minus the mass, which we know. Okay, how are we going to deal with this mass of helium now? Is the amount of helium, the mass of helium, connected to the volume of the balloon in any way, shape, or form? In other words, if the balloon gets bigger, do we need more helium? Yeah. And if the balloon gets smaller, do we need less helium? Right. Okay. So is there a connection between mass and volume? Density! So the density of helium will be mass of helium divided by volume of helium, which means that mass of helium can be written as density of helium, volume of helium. All right, so let's get that in there. Density, helium, volume, helium times G. Ooh! Ooh, what do I have in every term?
density,
Little g. So if it's in every term, then I can cancel it out? And what does that mean? This works anywhere that has an atmosphere. So we just solved the problem for Venus too, and Titan, and Jupiter, and Saturn, and any other planet that has a gaseous atmosphere. That's exciting. There's plans, by the way, to send balloons to Venus and float them in the Venetian atmosphere and do some really, really cool science. All right, let's see. We got density of air, which is given density volume. Oh, okay. So volume of I see volume of helium over there at the end, which is something that I want, right? But what's the volume of air displaced? How am I going to figure out what that is? What do we know about balloons in air? Are they partially or completely submerged in air? They're completely surrounded by air, right? So what has to be true about the volume of air pushed out of the way and the volume of helium in the balloon?
they have to be the same.
They have to be the same. Again, that only works when something's completely submerged. If you're partially submerged, you got to put the fraction on there. But here, these are going to be the same. So I'm just going to call it volume of the balloon. Okay? Minus mass of the balloon, minus mass of the antenna, minus density of helium, volume again of balloon. Since volume helium, volume air, and volume balloon are all the same thing for this problem. All right, so looks like the only unknown I have is the volume of the balloon. So I've got to do some algebra. Let's see, that's mass balloon, mass antenna. Moving over there. Let's get the volume of the balloon factored out over here. Density of air minus density of helium. And then I divide both sides. Density of air minus density of helium. So the volume of my balloon is going to be mass of the balloon. 600 plus mass of the antenna, 4,000. All divided by the density of air. 1.2 minus 0.179 for the density of helium. Since everything's in standard units, I'm going to get a volume standard unit out, which is a cubic meter, which is 4.14 times 10 to the 3 cubic meters, or approximately 4,000 cubic meters. Okay, so 4,000 cubic meters. This room is approximately 10 meters by 10 meters by 3 meters. So this room is about 300 cubic meters. Okay? The balloon needs to be 4,000 cubic meters, or about 13 times bigger than this room.
Wow.
Yeah. How many rooms are in this building that are this size? About 15. So that means the balloon has to be approximately the size of this building. Crazy, you say? I hold in my hands BBC News. Broadband net goes stratospheric. Airships in the stratosphere beaming back broadband may seem like fantasy, but tests in Sweden have suggested it could become a reality. Successful trial of the technology led by the University of York. Trials using a 12,000 cubic meter balloon. 3 times bigger than what we calculated, right? Because they're going to go way up high. And what happens to the density of air as you go up? Where's air most dense? Down low or up high? Down low, right? Okay. So as you get higher and higher, the air gets less and less, which means you need more balloon in order to float it. 12,000 cubic meter balloon flying at an altitude of 24 kilometers for 9 hours prove that it can successfully operate, blah, 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 blah. This article was published in October of 2005. Have any of you seen any internet zeppelins running around providing? Does anybody know what happened in like between 2006 and 2008 to internet service? It was called LTE. And it became, internet not only became, on cell phones became faster, but it became much easier to deploy from cell towers and much more reliant. And so this kind of technology, Google, Facebook, other companies were working on plans for doing high altitude balloons and wireless stuff. And it just became too expensive compared to the LTE rollout. Now we've got 5G and the cellular networks and all that kind of stuff. So no Zeppelins doing internet. But just so you know, these balloons are real. This is a picture of Felix Baumgarten. He was the first person to ever break the speed of sound in free fall. No aircraft. He was in a spacesuit, but he was not in a aircraft of any kind. He jumped out of his capsule there at approximately 120,000 feet above the ground and free fell for, I think it was 6 minutes or something like that. About 3 minutes into his fall, he broke the sound barrier, right? While falling. Incredibly dangerous. He spun around a lot, blanked out a couple of times, but did successfully make it and pulled his parachute. But this is a picture, so this is a graphic of how big the balloon was just to get him up to 120,000 feet, okay? That's a picture of it going up, right? You can see it's kind of partially inflated. When these balloons take off, they look empty almost, like they just don't look very full. They've got the buoyancy to lift it up. They just don't look full because by the time they get up high, they need to be at their full inflation, right? Because the density is getting less. But because it's so meaningful for us here in California, there's a picture of the Statue of Liberty. And in case you didn't know, the Statue of Liberty is tall, right? Okay, 300 feet tall, or about 100 meters. So that balloon, okay, was about as tall as a football field is wide, right? Okay, so we're talking enormous thing flying up there. It took him about 6 hours to get up there, sitting in that, what is amounts to basically a very large soda can. It was very thin aluminum metal.
Does the volume of air, like in a bag of chips when you're going up to the mountains, does it get more?
Yeah, well, it expands, right? Because the pressure outside the bag is less. If it was bagged at sea level.
So that still counts as more volume?
Yeah, volume increases. And we'll get to ideal gas law and pressures and all that kind of stuff in a bit. But yeah, the calculation we just did was not facetious or silly, okay? That's a lot of helium and a lot of sad clowns that can't fill up their balloons, right? All right, so everything that we've done up to this point is referred to as fluid statics. In other words, our fluids haven't been going anywhere. We've had objects sitting in them, the forces have been balanced on them, and the fluids themselves has no velocity. But what we're going to do now is we're going to switch and get some fluids to move. And these moving fluids, fluid dynamics, cause some really interesting things to happen. And when a physicist says really interesting things are happening, usually what we mean is very hard things are happening. But that doesn't make them any less fun. Fluid dynamics is a science that, believe it or not, is kind of relatively young because it really requires supercomputers to do. The interactions of fluids with objects as the objects either move through the fluid or the fluid moves around them requires some very scary math that really can't be solved by hand. There's too many things to keep track of. So supercomputers in large were invented to solve fluid dynamics problems. We're going to take, of course, a slightly easier approach to this, one that doesn't require supercomputers or modeling or really nasty differential equations. And I'm gonna flip my normal kind of way that I would present information to you. I like to give you a conceptual like framework and ideas and pictures that we then can overlay the math onto to be able to have predictive power. I'm gonna flip that. I'm gonna give you the math first. And then we're going to get into sort of the implications of what the math is telling us. Daniel Bernoulli was an Italian mathematician, and well, he was a physicist. He considered himself a physicist. He had a brother who was a mathematician. And although they respected and loved each other, they couldn't help but have sort of that brotherly competition, right, between each other. Daniel Bernoulli was responsible for one of my absolutely favorite quotes of all time, out of science. He said that the world. He was asked by somebody, "So what do you think of your brother's work?" and blah 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 blah. And Daniel Bernoulli responded, "The world would be a better place if there were fewer mathematicians in it." I guess that's what accounts for a 16th century sick burn, huh? Yes?
Are these pressure or flow?
Good question. Okay. What I'm writing down here is Bernoulli's equation. Okay? In a form that's useful. You might see it in slightly different forms where it says P1 plus 1 half rho V1 plus rho G8 equals constant. That's not a very useful form. Write it down this way. This is called Bernoulli's equation. And to answer your question, this is a pressure equation. And you know it's a pressure equation because that first P there, that capital P is pressure. And you can't add things together unless they have the same units. So the pressure is going to be in pascals, and then this 1/2 rho V1 squared, whatever that is going to have units of pascals. And then the rho GH, which we've already seen, right? The rho GH from the depth of water, right? That we already know has units of pascals. So everything has units of pascals in here. And so it's all about pressure, but there is something about Bernoulli's equation that hopefully looks a little bit familiar. The symbols, you might not have seen all these symbols together in the same place. But it should be tugging on your brainstem just a little bit. 1/2 rho V squared. Yeah, that feels kinetic energy-ish, doesn't it? Like, we know kinetic energy is 1/2 mv squared, right? But we know in fluids we don't use mass, we use density instead. So it's like we've got something that's 1/2 mass-ish times velocity squared. So that term, even though it's got units of pressure, feels very kinetic energy-ish. And there's 1s and 2s on here, isn't there? And we've used 1s and 2s before, right? Like initials and finals, comparing 2 points in something. So again, that conservation of energy kind of idea, although this isn't energy, this is pressure, right? And then to really top it all off, what does rho GH feel like?
Potential energy.
Feels like potential energy, doesn't it? So what we're going to do is we're going to approach this not as a new toolbox, but as an old familiar one. Where yes, the symbols are different. And we need to remember that we're talking about pressures in the end. But in terms of how we are going to approach the problem, we're going to look for like initial and final, a 1 and a 2. We're going to define zeros, right? We're going to just compare 2 points and not worry about what goes on in between and see what happens. There is another equation that is a partner, a companion equation that goes along with Bernoulli's equation. And my iPad decided that it didn't want to reconnect. 1 second. We are experiencing technical difficulties. What? Okay, the internet did this yesterday too. For some reason, at right about 8:30, the Wi-Fi decides to switch up all of the IP addresses. Are we done yet? No. You found your new IP address. How's your day going so far? Does it feel hot in here? No? Does it feel muggy? No, just, yeah, it does. A little bit. Some of you are like, no. Yes. Humans can't agree on the weather. They can't agree on anything. All right. Let's see. Refresh your IP address. Go for it. You can do it. Okay, good. We only got one. It's not that one. Okay, good. You got the right one. Here we go. Sorry about that. Here we go. The companion equation that goes along with it, and where did it go? No, that's not it. All right. There. Come on. You can see it, yeah. The companion equation that goes along with it is called the equation of continuity. This is there's kind of another statement along the lines of energy conservation, but this is more about how water, the amount of water you have flowing, say, through a pipe, has to stay the same no matter how the pipe changes its size. Yeah.
Are we using volume or?
Those are velocities. Those are supposed to be. See how I've done little like kind of almost curly V's there, right? The curly V's, lowercase V's are velocities, and then like an uppercase sort of straight V.
Are we using any volume for this equation?
There are no volumes in this equation. These are all velocities. Remember, this is fluid dynamics now. We're moving stuff around.
Right.
The equation of continuity says something like this. We'll use gallons per minute. So let's say you got a garden hose, and the garden hose can do 10 gallons per minute, okay, of water coming out of the garden hose, right? If you attach your garden hose to a bigger hose, can that bigger hose produce more than 10 gallons per minute? If 10 gallons per minute is flowing in, can the bigger hose magically make more water to cause? No, it can't, right? But what's going to happen is your small hose will push water pretty fast, and when it gets into the bigger diameter hose, the water is going to slow down. See how there's areas on there? The bigger the cross-sectional area, the slower the water will be moving. We've got to keep the amount of water flowing per minute, the volume. This is a volume flow rate equation because area has units of meters squared, and then velocity has units of meters per second, and that's the same as a cubic meter per second. So this equation of continuity just tells us that we can't be magically creating water out of nothing. Whatever water you've got flowing in your pipe, volume per time, must stay consistent regardless of how the size and shape of the pipe changes. All right, that's the equation. Now let's talk about the implications and how to use it. And I think I want to do this by doing the example of a siphon. And I brought one. Move this stuff out of the way so it doesn't get wet. There. Okay. So what I have right here is a container of water. Okay. And bucket. Mario, you're gonna get a little bit wet, it'll be alright. I'm kidding. Maybe. Go, and I got a hose. Alright, so what I'm gonna do is I am going to drain, right, okay, the water out of this bucket by just using this hose, okay? How am I gonna do that? What does a siphon do? How do you start one?
Pressure.
You put the, right, and then you have to suck on one end, right, okay? I may or may not have ever done this with gasoline, okay, right, okay? So here we go, right? So I get one end inside, right, and I suck on the other end to get the water flowing. Come on. I really don't want the water in my, it's Fresno City College water. Here we go, okay? So now I've got the water flowing. But if I bring the end of the siphon up too high, it stops flowing, right? Okay? But if I bring it down below the surface, woo, of the water, it starts to flow again. And if I bring it up high, do you see how it slows down? But if I bring it further down, it speeds up. So there must be a connection between where I hold the end of the outlet and the surface of the water. Indeed, what can you tell me, come on, about the level of the water in the container and the level of the water inside of my hose? It's the same, right? So the only way I can get water to flow out of this hose is to do what? Bring it below the level of the water inside of the container, right? Also, I don't know if you can see it from where you're sitting. You see how the stream of water narrows as it falls? It starts wide and then gets thin, okay? That's the equation of continuity acting. As the water drops out of the end, what happens to the speed at which it's falling? As it falls, it slows down? Speeds up, right? Got falling water, gravity's going to accelerate it down. So it's moving faster. The equation of continuity tells us the faster it flows, the smaller the area would have to be in order to keep the same amount of water, right? We've got a certain amount of water that's flowing out of the end, and if it speeds up, I've got to shrink that area down. So you can see that. You can go home and do that in your bathroom. Just turn on a stream of water. Make sure it's laminar flow. It's not turbulent. It doesn't have bubbles in it. And you can see the narrowing of the faucet water as it falls. Okay, let me do this again. Back up. It's a little bit wet up here. Be careful. All right. So I want to show you that it's possible to start a siphon without having to suck on the end. Okay? The only thing a siphon needs in order to work is for one end to be lower than the surface of the fluid in your tank. Okay? The reason you suck on it is not to get the fluid moving, it's to get the fluid into the pipe to begin with. So if you take your hose and you stick it in, and you're careful about how you do it so that your hose doesn't flip up to the, stick down, jeez, doesn't flip up to the top, okay, but stays under the surface of the water the whole time. Stay down there, good, all right, good, stay down there, all right. And so basically what I'm doing here is I'm being very careful and I'm completely filling my hose with water. Okay, and then I just plug up the end of the hose, I bring it over here, and I make, don't flip up there, and I let go. The siphon will work, right? Just like it did before. Sucking on the end of the hose, okay, just gets fluid inside of the hose, right? That's all that's necessary. The siphon will start itself as long as one end is lower than the surface of the water. Okay, so that's what a siphon is. Let's do the math of a siphon and see what happens. We are going to assume one thing. It's something I wasn't able to demonstrate for you right here. But let's pretend that what we're going to do is we are going to drain a really large container of water. So like we're talking swimming pool size, right? And we're going to do it with a garden hose, right? So in other words, we're going to assume for our siphon, and this is true for like water towers and municipal water supplies and all that kind of stuff, that the amount of water that we're trying to siphon off and the speed at which the water flows out of the end of the siphon, okay? The water level in the pool isn't changing very fast. So either you can be comfortable with the fact that if only a little bit of water is flowing out, that pool is not going to drop very fast. And so effectively, the speed at the surface of the water here is going to be 0. Or, if it makes you feel better, you could think of it like a municipal water supply where they have a faucet that's just adding water as it goes, keeping the level in the pool the same. I don't care how you think of it, but we're going to make an assumption, unlike what I had here where that fluid level was dropping, okay? We're going to assume that the fluid level in our tank is staying the same. And we're just drawing water out and letting gravity do the work for us. So to do the siphon, we're going to write down Bernoulli's equation. 1/2 rho g 1. So you got 1's on one side, 2's on the other. V2 squared plus rho g h2. There we go. All right. So this means we need 1's, 2's, and 0. Like we need to pick 2 points and set a 0 point. Let's do the 0 point for heights first. You know me, I like to pick lowest points in the problem. So that's exactly what I'm going to do. The lowest point in the problem is going to be down here where the water squirts out of the end of the pipe. Okay? So that'll be my 0. Which means that the height, right, of the water above that point, I'll just say is variable h, because I can move the end of my siphon up and down, right? But wherever that siphon is the lowest point. And then we're going to compare that again with the surface of water because that seemed to be a really important thing in our experiment. I'm going to call point number 1 to be the surface of water in the tank, and I'm going to call point number 2 to be where the water is exiting from the end of the hose. Just like conservation of energy, we want to pick 2 points where we're either trying to find something or we know something. We know something about the surface of that water. We know it's not moving. And as far as down at the end of the siphon is concerned, we are going to find out how fast the water is flowing out of the end of that pipe. That's our goal. We're going to do it using Bernoulli's equation. Okay, so we got 1's, we got 2's, we got 0's. Now we just got to move through this equation and start asking ourselves some questions. Like, what is the pressure at point number 1? At the surface of the water in the tank, what's the pressure if there's just air sitting on the top of that water? Is that water in a vacuum? No. So what's the air pressure going to be at the surface of that water if we're not told anything else? Yeah, it's easy to forget. Does air have pressure at sea level? Is there a weight of air sitting on top of that water? There certainly is. And what is that pressure? Well, it's like 1 atmosphere, or the reference pressure, right? Don't ever forget air pressure sitting above a body of water, right? It's not a body of water unless it's in air. If it's a body of water in a vacuum, we call that boiling water. Okay. 1/2 rho V1 squared. Okay. What is V1? How fast is the water moving at point 1? 0. So this whole term is 0, right? Because V1 is equal to 0. All right, and then does point number 1, is it at the 0 point for height? No. So it's going to be rho g, in this case, h. Okay. At point 2, where the water is squirting out into the air, what's the ambient pressure going to be? Not that hard. It's in air. So it's going to be air pressure. There's no significant difference between the pressure at the surface of the tank and the pressure where the water is squirting out. Okay, is the water moving down there at point number 2? Yeah, that's what we're trying to find, right? We're trying to find out how fast the water comes out. So we can't get rid of that term. And what's the height at point 2? It's nice 0, because that's where we put 0, right? So rho GH2 is going to be 0. Okay, what am I left with? Oh, first of all, atmospheric pressure appears on both sides of the equation, doesn't it? So I can subtract one from the other, and basically they'll cancel each other out. All right, that leaves me with a statement. That leaves me with rho GH equals 1/2 rho V squared. Okay. What's the same on both sides of the equal sign there? I'm gonna turn this around. 1/2 rho V, because that's the thing I'm solving for, equals rho GH. So the rho, okay, so it doesn't matter if this is water or alcohol or honey or anything else, right? The density of the fluid doesn't matter. That's interesting. Okay. What do I do with the 2? I've got a 1/2 V squared on the left-hand side. How do I get rid of the 1/2? Multiply by 2 on both sides? So if I do that, I get V squared equals 2GH. And then to get V, square root? V equals the square root of 2GH? Wait a second! We've seen that before! Where have we seen square root of 2GH before? How fast is this ball going to be going if I just drop it? Square root of 2GH. Remember we kept getting it over and over and over again in conservation of energy? The speed at which anything is going, whether it rolls down a ramp or gets dropped straight down, if it leaves with 0 speed, the speed it's going to have at the bottom is the square root of 2GH. What the heck is that doing here? What question did we ask? How fast does water flow when it falls through a height h? That's what a siphon is. If the height is 0 between the water level and the end of the siphon, if your inclined plane is flat, there's going to be no velocity. But if you tilt it, if you give the water a difference in height to flow through, there can be really only one answer for how fast it's going to flow, and that is the square root of 2GH. I'm only kind of kidding when I tell you, if you don't know the answer to a question, just answer the square root of 2GH. You've got a better chance of being right than guessing. Okay? This is one of those things in physics where we physicists sort of stand back and go, wow, where did that come from? Why did that happen? And you know what? We must be onto something. We're getting the same, and even though we're coming at it from a completely different conceptual framework, the underlying relationships between gravity, how it moves things, how fast things want to go. In the absence of friction, we're going to keep getting these answers. But again, it's one of those testaments that, we might be on the right track here. We're either totally, completely wrong, or we are discovering things about how our natural universe works. I just love things like this. It makes me excited. All right. That leads us to Bernoulli's principle. And Bernoulli's principle is the consequences, okay, of Bernoulli's equation. And again, starting a little bit with the math, just Bernoulli's equation again. Let's say we got a pipe, okay? And this pipe changes its cross-sectional area. So it's got a big area over here, and it's got a little area over here. It's like a circular cross-sectional pipe, okay? And we've got water flowing over here on this side, V1, right? We got water flowing over here. Equation of continuity is going to tell us things. So here, right, if A2 gets smaller, what does V2 have to do to compensate in order for that equal sign to be true? It's got to get bigger, right? So the fluid will move faster in the smaller section of the pipe. And you've experienced this. Let me make this vector just a little bit longer. You've experienced this whenever you've used a garden hose. So if you've been outside and you're watering the lawn or the garden or some flowers or something like that, okay? And you're squirting the bush or your little brother, or whatever target of opportunity has come into view, right? Okay, and you need to extend the reach of the water stream. You're out of hose, right? How do you get the water to squirt further? You put your thumb over the end of the hose. What did you just do by putting your thumb over the end of the hose? You made the area smaller, but the same amount of water has to come out. And so by making the area smaller, you make A2 smaller, V2 gets bigger, right? The water squirts further because it has more initial velocity as it comes out the end of the hose. So that's kind of what we're doing here. But Bernoulli's principle involves Bernoulli's equation as well. So we've got our in here. I'm going to, let's see, V1 squared plus rho G H1. Notice that my pipe, as I've drawn it here, does not change its elevation. That's supposed to be a G. H2 right there. The height of this pipe is 0 all the way across. So I can cancel both of those terms out. They don't change. They're the same. All right. We know the velocities are different. So let's move some stuff around. We're going to do P1 minus P2. I just brought the P2 over from the other side. Comes up negative. And then over here, it's going to be 1/2 rho V2 squared minus 1/2 rho V1 squared. Okay, what is that trying to tell us there? Which of these is bigger, V2 or V1? V2 is bigger. So that means 1/2 rho V2 squared minus 1/2 rho V1 squared is going to be a positive number, right? We've got a bigger number minus a smaller number. A positive pressure difference between P1 and P2. P1 has a bigger pressure than P2. Even though the smaller section of pipe sped up, the pressure in the bigger section of pipe is bigger. If you think about that for just a little bit, that sounds nuts. What Bernoulli's principle states is that the faster a fluid moves, the lower its internal pressure becomes. What? Wait a second. The faster a fluid moves, the lower its internal pressure? That's exactly right, and I'm going to prove it to you. But before we get there, let's figure out why your brain is a little bit confused. We tend to think of pressure as like when water strikes us. So like if I go and I get a garden hose and I squirt you, you'd be mad, right? You'd be wet, you don't want to be wet, you'd be mad, but it wouldn't hurt, right? If I went and got the fire hose and opened up the fire hose on you, you'd be mad and hurt, right? Because the fire hose, the pressure in a fire hose is way bigger than the pressure in a garden hose. Am I doing that today?
Yes.
Okay, so that's at 11, right?
Yeah, whenever you're.
Okay, perfect. So the pressure in a fire hose and I gotta go do a nuclear physics thing for the test. The pressure in the fire hose is much bigger than the pressure in the garden hose. That's they need high pressures in the fire hose to get the water onto the burning buildings and stuff, right? That is not the kind of pressure we're talking about. You're thinking of like the water striking you. That's a conservation of momentum thing, right? You got force, yes, there's area, you calculate the pressure. We're talking about the pressure inside the stream of fluid itself. The internal pressure of the fluid. That is what gets lower the faster a fluid moves through a pipe. And I can prove it. This is something you can do at home, okay? Take 2 pieces of paper, okay? And you wanna hold them up so that they are like, I don't know, an inch or 2 apart from each other, okay? So you're just gonna the way I do this over time, I've learned that if you hold the pieces of paper like in your hands like this, okay? And you kind of rest your thumbs together, you can get a pretty stable situation where you're just kind of hanging pieces of paper like this, right? Nice and vertical, kind of close to each other. And then what you're gonna do is you're gonna take a big deep breath and you're gonna blow between them. Give it a nice steady stream of air. Be honest, don't move your fingers. Come on, hold up. I didn't move my fingers. What's the paper doing? What does it do? It comes together, doesn't it? Why does the paper get pushed together as I blow between the pages? Where's the lower pressure? Outside or in between? Where's the fast-moving fluid? It's in between the pages. So if I have a fast-moving fluid in between the pages, and no fluid moving outside the pages, or very little, then I'm going to have high pressure out here, I'm going to have low pressure inside, and the pages will get squeezed together. I brought with me a leaf blower, okay? Good for blowing leaves, but also good for moving fluids at very high rates. The speed that the air comes out of here is about 150 to 200 miles an hour, okay? Notice we got the kind that's got the fan mounted horizontally, so we have no problems with moments of inertia. Okay, so what I'm gonna do, now I'm not gonna be able to talk while this is happening, so I'll just have to explain a little bit ahead of time. But I'm gonna take a very fast, right, fluid here, and then I'm going to put my beach ball in that stream. And I want you to watch and see what happens. What? Why did the ball just float there? Where was the fast-moving fluid? Here's the ball. Air is coming up, right? So it comes out of the leaf blower, it comes up, and it's forced to go around the ball. There's a bunch of fast-moving fluid around the ball. Slow out here, fast right here, right? So the ball will sit in a zone of low pressure. The faster a fluid moves, the lower its internal pressure. The fast-moving fluid surrounding the ball, that means the pressure higher outside, lower to the inside, and you've got a ball that will float in that stream of air. Until I got it too far, right? And then gravity was able to take over, right? The pressure differential wasn't enough to keep gravity from winning, and it fell out. This idea, this fluid moving fast and having a low internal pressure, is responsible for a lot of things. It's responsible for how boats can sail against the wind. Like, you need two sails to do it. Airplanes, being able to fly. Cold legs in the shower. What does that have to do with Bernoulli's principle, Mr. Balogh? There are basically two kinds of people in this world. People who take showers in the morning and people who take showers in the evening. Let's pretend for the sake of argument here that you are the kind of person that takes a shower in the morning, okay? So this, you've just woken up. A lot of people are not awake when they get out of bed. So you're stumbling around, half aware of your surroundings, right? And you get in the bathroom and you turn the water on, right? Now, I just want to point out, all of you morning shower people, if you're already in the shower and you're turning the water on, you've probably invented some sort of stance or dance that you do to keep the cold water from hitting you. I just want to point out that you can turn the shower on before you get in. Try to hold on to that thought when you wake up next, right? Okay, just you can avoid the whole situation if you just turn it on, let it heat up. Okay, so now you're inside the shower, right? Nice warm stream, and you're sitting there, right? Oh, the warm water. Okay, I can wake up now, right? When all of a sudden the cold, wet, clammy hand of death reaches out and grabs your leg. What am I talking about? The shower curtain has attacked. I can tell that some of you have had this experience, okay? Where you were minding your own business and that cold plastic fabric shower curtain it's encroaching on your personal space, isn't it? You got this big, it's like coming at you. Why is the shower curtain attacking? Where is the fast-moving fluid? It's in the shower, isn't it? You've got that shower head, right? And that water squirting down on you and it's pulling the air molecules with it. So you have a faster moving fluid inside the shower. Outside the shower, the air is hardly moving at all. So high pressure out there, lower pressure inside where the fast moving fluid is. The pressure differential is going to be towards the inside of the shower, and the shower curtain's not going to really have any choice. It can't fight back. And so it's just going to be pulled inwards. That's why when I became a homeowner, all of my showers had doors on them. I did not want to hear screaming in the morning, right? Screaming in the afternoon's fine. Screaming in the morning, not going to happen, right? Shower curtains have a lot of benefits over doors. They're cheaper and easier to fix and all that kind of stuff. But one of the ways they avoid having screaming in hotels in the morning is they do a trick. This is mostly a psychological trick, but it's also partly a physics trick. I'm going to exaggerate the effect here. So this is a cross section of a bathtub, right? We're kind of looking along the long axis of the bathtub, right? Well, you're not supposed to have that much water in a shower, right? Okay. The shower curtains, like in normal homes, they'll be mounted up here and they'll hang down kind of straight, okay, just like that. What they'll do in hotels is the ends of the shower curtain rod have to be at the same place, but what they'll do is they'll bend the rod out, okay? So instead of just being a straight bar across, they'll bend it out so that the shower curtain itself, and again, I'm exaggerating, is forced to kind of do that, okay? So you're standing in the shower, right, and it's like bowing out into the room even though it's fixed at the same exact point on either side. This does two things. Number one, it allows the hotel to lie or cheat and say that they have spacious showers, when in fact it's just a standard sized tub. it feels like there's more space in the shower because they've given you sort of more space up here, right? But secondly, notice that the vector for gravity, right, the center mass of the shower sheet is down right here in the center, pulling down and away, right? For the vertical sheet, there's no way for gravity to help that sheet not be deflected. But if you can get the sheet to hang at a slight angle, then gravity will help keep that sheet from billowing into the shower area. Psychologically, you feel like you have more space even though you don't, and gravity is helping fight that cold shower curtain coming after you. So Screaming in the Morning brought to you by Bernoulli's principle. Vascular flutter. What's vascular flutter? Does anybody know here what vascular flutter is? No. Physiologists, pre-meds. Vascular flutter is what happens when you have too much In-N-Out burger in a lifetime. Vascular flutter is what takes place when plaque deposits have built up on the insides of arteries and are beginning to close off the artery. So arteries are, well, they're tubes that carry blood, and they are very flexible structures. They can kind of grow, they can do all kinds of different things. But if you eat too much stuff that's got like fats and cholesterols and things like that, the plaques can build up on the surface of the arteries. And so now blood flow gets constricted in here. And the cross-sectional area of your artery is reduced. So what happens to the blood, the speed at which blood is flowing here at the constriction? It gets faster, right? Equation of continuity. So here, the speed of the blood picks up. Well, what happens when a fluid moves fast? What happens to its internal pressure? It goes down, right? And so the pressure in this artery drops. Higher pressure outside, low pressure here in the constriction, and the constriction, you can actually get it. The artery is flexible enough that the artery will like pinch itself off. The walls of the artery will kind of collapse, and the plaques will touch, and it'll flow so fast, and the pressure will drop that it actually cuts off the blood flow. And so now you got a bunch of blood behind here, the heart's pumping, right? And it's trying to push, and it's like pushing, right? But all of a sudden it's come to a stop, right? So now there's no fluid moving in here. The speed is 0, the artery will rebound and open up, and the blood will all of a sudden go whoosh through the clog, and as it goes whoosh through the clog and speeds up really fast again, it'll wham, it'll shut down. It'll close itself off. And then the pressure builds up and it goes whoosh and then it slants. That repeated hitting of the arterial walls against themselves is called vascular flutter. You can hear it through a stethoscope. Okay? If you're a cardiologist and you know what you're looking for, you can actually park a stethoscope above an artery and hear the artery banging against itself. This is not a medical condition you want. Okay? But we can detect it thanks to Bernoulli's principle. There are so many places that fluid dynamics interface with our lives. I've just really broken the tip of the iceberg for you, and it's really all we need for this class. But realize fluid dynamics are everywhere, from the weather to how your car moves efficiently, through the pipes in your house. It's all over the place. That was the end of chapter 11, and we will start chapter 12 on Tuesday. Get ready for thermodynamics, temperatures, ideal gas laws, calorimetry, and the rest. If I don't see you tomorrow on grass, have a fantastic weekend.